We've learned that regular languages can be defined via finite automata, via regular grammars. A particular popular way to define regular languages are regular expressions. They are heavily used in programming languages or in system tools such as grep or SED in Linux, and they are used a lot in order to extract information, to extract certain pattern from text documents. So what are regular expressions? Regular expressions are syntax for regular languages. So a regular expression over an alphabet sigma is a word of one of the following forms. The empty set symbol, so this is now a symbol, it's not the empty set. The empty set symbol is a regular expression. The symbol lambda is a regular expression, and again, this is now a symbol, it's not the empty word lambda here. For every letter A of our alphabet sigma, the letter A is a regular expression. If we have two regular expressions R1 and R2, then R1 plus R2 is a regular expression. R1 times R2 is a regular expression. And if you have a regular expression R, then also R star is a regular expression. Now, this is just syntax, but of course the syntax has a meaning, and this meaning is quite close to what the syntax suggests. So we associate to each of these regular expressions, we associate a language. And of course, the language associated to the empty set symbol is the empty language. So we are overloading notation here by using the same symbol as the language, but I hope it's not confusing because the meaning is quite close to the symbol. Also, the interpretation of the symbol lambda is the language that just contains the empty word. So it's not the empty language, but it's the language that contains just a single word, the empty word. The interpretation of a single letter is the language that just contains the word consisting of the single letter. So the language of the regular expression A is the language that just contains the word A. The language of R1 plus R2 is the union of the languages of R1 and R2. So the symbol plus is translated to the union of languages. The language associated to R1 times R2 is the concatenation of the two languages, of the language of R1 concatenated with the language of R2. And recall what this meant. It means that we concatenate every word from the first language with every word from the second language. And the language of R star is the language of R to the power star, so that's the Kleene star, meaning that we take the language of all the words that can be built from the basic building blocks in the language L of R. Let's have a look at a simple example. Here we have a regular expression A plus B times C star. So what language is associated to that? A gives rise to the language just containing the word A. B gives rise to the language just containing the word B, and likewise for C. A plus B is translated to the union of these two languages. So the union of the language just containing A and just containing B is the language containing the word A and the word B. The times in the regular expression translates to language concatenation, and the star translates to the Kleene star. So if we have a language just containing C with a Kleene star, we get all the words that just contain the letter C. So we get all words that start with A or B followed by an arbitrary number of C's. Regular expressions are heavily used for searching and manipulating text. So regular expressions can be used to search pattern in text and to replace pattern in text. So for instance, this is done in the Linux tool grep, which is basically purely based on regular expressions, but also in scripting languages such as Perl or Python, regular expressions play a major role. In basically every major programming language, there is a library that allows you to work with regular expressions, because regular expressions are really convenient if you're trying to extract data from text. Let's have a look at one more example. So we are asked to find a regular expression that gives us all words over the alphabet AB that contain the subword BAB. So how should this regular expression look like? Probably in this regular expression we should somewhere have B times A times B, because we want to make sure that the subword BAB is in there. But we also want to express that this subword BAB does not need to appear at the beginning of the word. So before BAB there can be anything. How do we press anything in a regular expression? Anything, so meaning an arbitrary word, can be expressed by taking A plus B to the star. So we can write this, we can write A plus B to the power star, and this will give us all words over the alphabet AB. Because A translates to the language just containing A, B to the language just containing B, plus translates to the union, so we get the language consisting of A and B, and if we then take the cleaning star, we get the language of all words over A and B. So we have any word on the left, then we require that there must occur the pattern that we are looking for, BAB, and then we follow with any word on the right. So this regular expression gives us all words over AB that contain the pattern BAB. And for convenience, we will typically suppress this dot. So we will usually write this regular expression simply as follows, just by writing A plus B star, BAB, A plus B star. So we will, in most instances, we will suppress this dot because the regular expression is easier readable like this, and it's clear that between any two expressions there must be a dot. We are now going to prove that a language is regular if and only if there's a regular expression that defines this language. And there's again two directions that we need to establish. We need to show that every regular expression, the language of this expression is regular. In order to do this, we will take an arbitrary regular expression and we will show that it can be translated into a non-deterministic finite automaton. And the other direction is from left to right. We have to show that if we have a regular language, then this language can be defined by a regular expression. So we will take an arbitrary non-deterministic finite automaton and we show that this can be translated into a regular expression. So we will now be concerned with proving both of these directions. We are starting with the translation of regular expressions into non-deterministic finite automata. So we are now going to translate regular expressions R into non-deterministic finite automata M, such that, first of all, the language of the automaton is the same as the language of the regular expression. And we want a second property, and this second property we would like to have because this is an inductive construction. We want to know something about the translation of the sub-objects, so the smaller regular expressions. And what we want to know is, namely, we want to ensure that the automaton that we construct has precisely one final state and precisely one starting state, and the final state is different from the starting state. And the second property will be important for the inductive construction. So now let's start. We have to look at the different forms that a regular expression can have. These are all the forms that a regular expression can have. The first form we look at is the empty set symbol. The language associated to this is the empty language. So the question is, how do we define a non-deterministic finite automaton that accepts the empty language, so does not accept anything, but still has one starting state and one final state that are different from each other. So the simplest automaton we can pick is this one. We have a starting state, no transitions. This starting state is not a final state, so this automaton does not accept any word. It accepts the empty language. And we have a separate final state. So this is an accepting state, and you may wonder why did we add this. We added it precisely because of the second condition, that any automaton we construct should have a final state. So it's a final state, but it's not reachable at all. Now, how do we construct an automaton that accepts the language just containing the empty word? We can take basically a very similar automaton. All we have to do is we have to add a lambda transition from the starting state to the final state. So this automaton still has just one starting state, one final state, and it accepts only the empty word. There's no other letters that it can read. In order to make an automaton that accepts the language that just contains the word A, we can use the same construction as for the empty word, but now we replace the lambda by the letter A. So this automaton can read the letter A, then it accepts, but it does not accept any other word. It does not accept the empty word, and it does not accept any word that has more letters than just the A. Okay, so this is our base cases. Now we will look at the inductive cases. So if we want to create an automaton for R1 plus R2, we assume that we have already translated R1 and we have translated R2 into non-deterministic finite automata, and we assume that they have these properties, namely that they have one starting state and one final state that are different from each other. So now we construct a new automaton. So this is the automaton for R1. We assume that we have already created this. This is the automaton for R2. We assume that we have already created this. And now we construct a new automaton from them. We add a fresh starting state and a fresh final state. We add lambda transitions from the fresh starting state to our old starting states of R1 and R2 respectively. And we add lambda transitions from the old final states of R1 and R2 to our new final state. So this dashed line here means that this was a final state before, but now we make this one here the only final state of our new automaton. Now, why does this automaton accept the union of these two languages? So we start in this starting state, and now we can choose whether we want to accept a word from the language R1 or a word from the language R2. We choose one of them, then we read a word from R2, or if we've chosen R2, from R1 or R2 respectively. Once we read the old final state, we have a lambda transition to our new final state. So that means any word of R1 can be accepted in the new automaton, and likewise any word of R2 can be accepted in our new automaton. So it's not difficult to see that this automaton indeed accepts the union of the languages of these two subautomata for R1 and R2. And likewise, we can construct an automaton for the regular expression R1 times R2. So what should this automaton do? It should accept the concatenation of the languages of R1 and R2. So we create a new automaton. Again, we assume we have already translated R1 into an automaton and R2 into an automaton. We keep the starting state of R1. We keep the final state of R2. But we make the final state of R1 no longer final, but we add a lambda transition from the old final state of R1 to the old starting state of R2. So that means if we want to accept a word in this automaton, we start in the starting state of R1, then we have to read a word in the language of R1, we end in the old final state of R1, take a lambda transition to the starting state of R2, which is now no longer starting state of the new automaton, we read the word of R2, and we end in the final state of the new automaton. So the words accepted by the new automaton are precisely those words that start with a word of the language of R1, followed by the word of a language of R2. So it accepts precisely the concatenation of the two languages of R1 and R2. Now for the cleaning star, so R to the star, we again assume that we have translated the regular expression R into a non-deterministic finite automaton, and we create a new automaton by adding a fresh starting state, a fresh final state, a lambda transition from the fresh starting state to the old starting state, a lambda transition from the old final state to the fresh final state, and lambda transitions from and to, so between the fresh starting state and the fresh final state. So the cleaning star means that we also should be able to accept the empty word. That works. We can take from the starting state, we can take the lambda transition to the final state, and we can immediately accept the empty word. We should be able to accept any number of times a word in the language of R. So how do we do this? We take a lambda transition to the old starting state of R. We read the word in the language of R. So we get to the old final state. And then we take a lambda transition to the new final state. So we can accept words in the language of R. And we don't need to stop here. If we want to use more building blocks, so if we want to accept something that is composed like of 3 words of R, then we can first read the word of R, then go to the final state, take the lambda transition back, do the same again, then we have read a second word of R, do the same thing again, a third word of R, and so on. So we can accept any word that is built from building blocks in the language of R. We can go an arbitrary number of times through this automaton that accepts words of R. Now, you may wonder, why did we add a fresh starting state and a fresh final state? Why not just take the automaton for R and add these lambda transitions from the starting state of R to the final state and back? On the next slide, we will see that the fresh starting state and the fresh final state are indeed crucial. Otherwise, we may accept words that we do not want to accept. The examples on this slide show that the fresh starting and the fresh final state are indeed needed. This first regular expression shows that we really need the new starting state, and the second regular expression shows that we really need the new final state. So let's have a look at that. So let's have a look at the regular expression A star B to the star. So the automaton that I've drawn here accepts the language for A star B. It accepts an arbitrary number of A's followed by a B. It has an initial state, it has a single final state, and they are different from each other. So this automaton fulfills the criteria of our inductive construction. Now we want to construct the automaton corresponding to the language of this automaton to the star. What do we do? The construction would say that we have to add a new starting state and a new final state. Now let's assume that we do not want to do this. Let's assume that we do not add a fresh starting state. We only add a fresh final state. Let's call it Q3. So this is now our final state. This state is no longer final. We have a lambda transition. Lambda transition from Q2 to Q3. And we now also need lambda transitions from this fresh final state to the starting state and from the starting state to this fresh final state. Let's do that. We add lambda transitions here. Can I not grab this? like this, and we need one more here. Again, the same problem. So, okay, so also this is a lambda transition, and this is a lambda transition. Now this is almost the construction as we had on the slides, but we did not add a fresh starting state. Now the question is this correct? Does this automaton really accept this language that we wanted to accept? So what are the words in this language? It's the empty word. The empty word is accepted. We can immediately go from the starting state to the final state. That's fine. And otherwise, it's all the words built from these basic building blocks. The building blocks consist of words that start with an arbitrary number of a's, followed by a b. So what goes wrong here is that we can read a number of a's. So for instance, this automaton can read the word AA. So the word we can read AA, and then we can take the lambda transition to a final state. So the automaton shown here accepts the word AA. But the problem is, the word AA is not in the language of this regular expression. Because if we have some A's, there always has to be a B following them. So this automaton accepts a word that is not in the language of this regular expression. The problem is that we have made a lambda transition from the starting state of our original automaton to the final state. And this allows us to escape from this automaton while the automaton was still computing, so to say. The automaton reads a number of A's and it should finish by reading a B, but now this lambda transition allows us to escape in the middle of the computation, so we can accept a partial word, we can accept some A's without reading the B. So this shows that we really need to add a fresh final state. Let's call it Q0. This is now our final state. We have to add a lambda transition from Q0 to Q1. And these lambda transitions, they should not go to Q1, but they should go from Q0 to Q3 and from Q3 to Q0. Now let's see what I can grab this like this. So this is a lambda transition and this is a lambda transition. So now this automaton, if we make this state non-final, this automaton is correct. This automaton accepts this regular language. It does not allow to accept the word AA. So once we enter this automaton, we really have to read a full word accepted by this inner automaton. We can read a number of A's, but we have to follow with a B before we can accept. So this is the reason that we need an additional starting state, and the second regular expression on the slides shows that we also need an additional final state. So in general, it's really important that we add a new initial state and a new final state. Now we're going to look at the other direction of the proof. Now we're going to translate non-deterministic finite automata into regular expressions. So we start with a non-deterministic finite automaton M, and we're going to translate it into a regular expression R, such that the language of the regular expression is the language accepted by the automaton. The construction consists of multiple steps. The first step is to transform our automaton such that the automaton has precisely one starting state and precisely one final state. If you recall how this is done, in order to make the automaton have precisely one starting state, we add a fresh starting state and we add lambda transitions to all the old starting states. And then we make this fresh starting state the only starting state of the automaton. And likewise, for making it have a single accepting state, we add a fresh state, we add lambda transitions from all the accepting states to this fresh state, and we define that the fresh state is the only final state of the automaton. The second step of the construction is the removal of double arrows in the automaton. From this point on, we consider the automaton as a transition graph that has regular expressions as the labels of the arrows. The removal of double arrows means the following. If we have states Q1, Q2, such that we have two arrows from Q1 to Q2, one arrow with label R1, another arrow with label R2, then we are going to merge these two arrows into one arrow with a label R1 plus R2. Note that Q1 can be the same state as Q2. So we also merge the arrows if we have two loops on some state. Then we merge these two loops into a single loop. And we repeat this merging of double arrows until there are no such double arrows left. So we keep merging until there are none left before we continue with the next step, with step 3. The third step of the construction removes a state that is neither a starting nor a final state. So we pick one state, Q, such that Q is neither starting nor final. If none such state exists, then we are finished with step 3 and we continue with step 4. Now we remove Q as follows. Before we remove Q, we have to make sure that Q is no longer needed. Q could be needed because it's part of pass through the automaton. So we have to make sure that if we drop Q, the language accepted by the automaton is not changed. How does this work? We have to add additional transitions. These red arrows here. So for every incoming arrow into Q and every outgoing arrow out of Q, we have to add an additional transition. So if we have an incoming arrow from Q1 to Q and an outgoing arrow from Q to Q2, we have to add an additional transition from Q1 to Q2, so bypassing Q, and the label of this additional transition is derived as follows. R1 is the label of the incoming transition, R2 is the label of the outgoing transition, and R is the label of the loop on Q if it exists. If there's no loop on Q, then we are adding an arrow of this form where there's no R star in the middle. Now we have to do this, we have to add these additional transitions for every combination of an incoming and an outgoing arrow from Q. So that means if Q has n incoming arrows and m outgoing arrows, then we have to do this n multiplied by m times. So let's take an example. Let's say we have 5 incoming arrows and we have 10 outgoing arrows. Then we have to add 50 additional transitions, 5 times 10, for every combination of an incoming and an outgoing arrow from Q. So we add all these additional transitions, and once we've done this, we can drop Q without changing the language of the automaton, because now these additional transitions take care that all paths through Q are covered. And again, note that the state Q1 can be equal to Q2. So we can have an incoming arrow to Q and an outgoing arrow from Q from and to the same state So Q1 equal to Q2. So after adding all these transitions, we can safely remove Q, and then we repeat step 2 and step 3 until there's nothing to be done. So after having removed a state, we go back to step 2 and remove all the double arrows. And this is important in particular because, first of all, removing double arrows saves work when dropping states, because we have to consider less incoming and outgoing arrows. But also we assume here that Q just has a single loop. So we have to have merged all the loops. So after dropping a state, we go back to step 2, we merge all the double arrows, then we continue with step 3 and look whether we can remove another state. And once we are done, once there's no more state that we can remove, we continue with step 4. The fourth step is the final step of the construction. It consists of reading off the regular expression from the automaton that we have obtained. So in this step we assume that we have completed step 2 and step 3, so we have removed all the states that are neither starting nor final. And we have removed all the double arrows. Since we have started with an automaton that has only one starting state and only one final state, we end up with an automaton that consists of at most 2 states. It will have 2 states if the final state is different from the starting state, and we end up with a single state if the final state is also the starting state. Now, let's first consider the case that we end up with 2 states. Then our automaton has at most 4 transitions. Because we have removed all the double arrows, there can be at most 1 loop on the starting state, 1 loop on the final state, and we can have forth and back transitions between the starting and the final state. Now we refer to the labels of these transitions. These are regular expression labels. R1 is the regular expression that is the label of the loop on the starting state. R2 is the regular expression on the transition from the starting to the final state. R3 is the regular expression on the transition back to the starting state. And R4 is the regular expression that is on the loop on the final state. Now, if one of these transitions is missing, so if one of these arrows is not present, then we can simply add this transition, and as a label we then use the regular expression that symbolizes the empty set, the empty language. Now, how do we read off a regular expression from this automaton? The idea is that we want this regular expression to capture all possible paths from the starting state to the final state. Now, this is the regular expression that we end up with, and let me explain how this is derived. First, we start in the starting state, and we can take an arbitrary number of times this R1 loop. So this gives rise to R1 star. Afterwards, in order to get to a final state, we have to take the R2 transition. This gives rise to this R2. Now we are in a final state, and we can continue with any path that brings us back to the final state. And there's 2 possible options here. For one, we can take this R4 loop. This brings us immediately back to the final state. This gives us this R4. And the other option is to take this R3 transition, then an arbitrary number of times R1, and then we have to take R2 to get back to the final state. This gives this R3, R1 star, R2. So these are the 2 options for path from the final state to the final state. And we can mix them in arbitrary ways. So we can take a number of times R4, then R3, R1 star, R2. So whatever we like, and we can do so an arbitrary number of times. In total, this gives us all the possible paths from the starting state to the final state. And if we now take the regular expressions that R1, R2, R3 and R4 stand for, and we fill them in the right places, then we get the regular expression that describes the language accepted by this automaton. Now, what happens if the final state is also the starting state? Then we end up with an automaton that has a single state that is both starting and final. Since we have removed all the double arrows, there can be at most one transition in this automaton. There can be only one loop on this single state. So let's say that the regular expression on this loop is R, then the regular language that this automaton accepts is just R star. We can take this R loop an arbitrary number of times and we will always end in the final state. So let's do some exercise. Let's try to find a regular expression that describes the following language: all the words over AB that contain an even number of A's and an odd number of B's. First, we are going to design a non-deterministic automaton that accepts this language. And then we are going to transform this non-deterministic automaton using the construction that we have just seen into a regular expression. This is a non-deterministic finite automaton that accepts all words over AB that contain an even number of A's and an odd number of B's. Actually, it's even a deterministic finite automaton. So how does this automaton work? I've named the states in a way that they describe what they stand for. The E stands for even and the O stands for odd. So we start in a state where there's an even number of A's and an even number of B's. In the beginning we have 0 A's and 0 B's. Now if the automaton reads an A, so then we have 1 A, we switch from a state where we have an even number of A's to a state where we have an odd number of A's. And we still have an even number of B's. If we read an A again, we switch back to a state where we have an even number of A's. If we are in this state and we read a B, then we switch from an even number of B's to an odd number of B's. If we read a B again, we switch back to an even number of B's. And if we're in this state, we read an A, we switch from an even number of A's to an odd number of A's. And if we read an A again, we switch back to an even number of A's. So this automaton remembers in the state whether we have seen an even number of A's, an odd number of A's, and whether we have seen an even number of B's, an odd number of B's. And we accept if the word contains an even number of A's and an odd number of B's. Now we want to create a regular expression that describes the language accepted by this automaton. Now the first step of our construction was to make the automaton have a single starting state and a single final state. And luckily the automaton is already in the good shape. We only have one starting state and we only have one final state. So there's nothing to be done in the first step. The second step is the removal of double arrows. If we have two states that have two arrows between them in the same direction. Also this step is at the moment nothing to be done. We don't have any double arrows in the same direction. We have here two arrows, but they are in different directions. So we don't have to remove any double arrows at this point. The third step is the removal of states that are neither starting nor final. We have two such states. This state is neither starting state nor final state, and this state is neither starting nor final state. Now we have the choice. We can either remove this state or this state. So let's say we pick this one. Before we can remove this state, we have to add additional transitions in order to make this state superfluous. Now, what transitions do we have to add? We have to look at every combination of an incoming and an outgoing arrow of the state that we want to remove. So we have one incoming arrow, two incoming arrows, and we have one outgoing, two outgoing arrows. So two incoming and two outgoing arrows. That means we have to consider 2 times 2 is equal to 4 combinations. The combination of every incoming with every outgoing arrow. Okay, let's start with this incoming arrow. We have an incoming arrow A and we have an outgoing arrow A. So we have to consider these two in combination. And this means that we have to add an additional transition from the source of the incoming arrow to the target of the outgoing arrow. So we have to add an additional transition from this state, from the starting state to the starting state. And what's the label of this transition? So we add an additional transition. And what's the label that this should have? The label should be the label of the incoming arrow. Then possibly if here would be a loop, then this loop to the star, but we don't have a loop, followed by the label of the outgoing arrow. So the incoming arrow is A, outgoing arrow is A, so we get AA. Okay, that's our first transition that we've added. Now let's look again. We have this incoming arrow and we have this outgoing arrow. So we have to add a transition from the starting state to this state in the bottom right. What should be the label here? Again, it's the label of the incoming arrow. Then we don't have a loop, so we immediately follow with the label of the outgoing arrow, so we get AB. AB from this state to this state. Okay. Now we have one more incoming arrow, namely this B arrow incoming and this A arrow outgoing. So we have BA. So we need to add the transition from this state to our initial state. What should be the label of this transition? It should be BA. BA. Okay. Now the last combination, we have an incoming arrow B and an outgoing arrow B. So we have to add a loop on this state. And the label of this loop is BB. The label of the incoming followed by the label of the outgoing, because we don't have a loop on this state. Okay. Now we can drop this state. Now we can remove this state because we have added all the necessary transitions to make this state superfluous. We've added 4 transitions. Now we have to go back to step 2 and we have to check whether there are double arrows that have to be removed. In this case, there are no double arrows that need to be removed. We still don't have any 2 states that have 2 arrows between them in the same direction. So we are immediately done with step 2 and we can return to step 3, removing a state that is neither starting nor final. Now we don't have a choice, we have only one state that is neither starting nor final, that's this one. We have to remove this state. And again, before we remove this state, we have to make it superfluous, we have to add additional transitions. This state again has 1, 2 incoming arrows, incoming from outside, so I'm not counting the loop, and it has 1, 2 outgoing arrows. So we again will have to add 4 additional transitions. 2 times 2. Let's start. we have one incoming arrow and one outgoing arrow. So we have to add a loop on this state. Now what should be the label of this loop? The label should be A followed by this loop to the star, so A BB star followed by A. So we get A BB star A. And these brackets are important because if I leave the brackets out, then it will only be B star, and then we can have an odd number of B's. Okay, this is our first transition that we have to add. Now we again have an incoming A arrow and an outgoing BA arrow. So the source of the A arrow is this state, the target of the BA arrow is this state. So we have to add a new transition from this to this state. Let's put this somewhere here. What should be the label of this transition? It should be A BB star BA. A BB star BA. Okay, very good. So we have treated this incoming arrow completely. Now let's look at the next incoming arrow. We have an incoming arrow AB. Let's look at the combination of this incoming arrow with this outgoing arrow. So AB, BB star, A. So we need a new transition from here to here. And the label of this transition is AB, the label of the incoming arrow. Then the loop to the star, BB star. And the label of the outgoing arrow, A. Okay. One more transition we have to add, and that's the combination of this incoming arrow with this outgoing arrow. So we have this AB arrow and then this BA arrow. That means we have to add an additional loop here. And the label of this loop is the label of the incoming AB, followed by BB star, followed by BA. Okay, now we have included all the transitions necessary to make this state superfluous. So now we can drop this state. Okay, so we have an automaton with two states, but before we can read off our regular expression, we have to go back to step 2 and we have to merge double arrows. So now let's check what are the double arrows that we have. We have one double loop on our starting state. So we can merge these two. So we just say that the label of this transition should be AA plus the label of the other transition. So we can now drop this loop. Now we have more double arrows here. We have this B arrow from the starting to the final state, and we have this arrow from the starting to the final state. So we add B here, and we can drop this arrow. We have two arrows from the final to the starting state. So again, we will add the B to this label. And we can drop this transition. Okay. Now we have an automaton that consists of two states, a starting state and a final state, so no more states can be dropped. We have merged all the double arrows, and these are the regular expressions on the remaining transitions. Now let's read off the regular expression. I've already written down here the regular expressions that we have along these transitions. So R1 is the expression on this loop, R2 is the regular expression on the transition from the starting to the final state, R3 is the regular expression from the final to the starting state, and R4 is the loop on the final state. Now, how did we read off the regular expression? If you recall, we can take an arbitrary number of times R1 followed by R2, so we can take this loop an arbitrary number of times followed by R2, and then we can take paths from the final to the final state, so we can take the loop R4, or we take R3 back to the starting state followed by R1 star followed by R2 to get back to the final state, and we can do this an arbitrary number of times. Now all we have to do is we have to fill in these regular expressions for the right variables here. So R1 is this regular expression, and we should not forget to make parentheses at the right places, because if you leave this parenthesis out, then the star is not applied to the entire regular expression. We have here 1R1, let's also make here parentheses in the correct way. Let's fill in R2. Put R2 here. We have R4 in this place. And we have one more R3, which again needs parentheses, and one more R2, which also needs parentheses because it contains a plus, and we're done. This is the regular expression that describes the same language as our original automaton. As we have started out with an automaton that accepts all the words over a B that have an even number of A's and an odd number of B's, this is also the language described by this regular expression. It describes all the words over a B that have an even number of A's and an odd number of B's. The second exercise on the slide I will leave as an exercise to you. If you recall, we have already constructed an automaton that accepts the language in question, namely all the words over a B that do not contain the pattern BAB. How did we do this? It's relatively easy to construct a deterministic automaton that accepts all words over a B that contain a subword BAB. And if you have a deterministic automaton, then you can get a deterministic automaton for the complement simply by flipping the final states. So make the final states you make non-final, the non-final states you make final. And then you obtain an automaton that accepts exactly the language of words over AB that do not contain the pattern BAB. But you have to be careful if you then try to transform this automaton into a regular expression, because this automaton will contain more than one final state. So what you first have to do, you should not miss step 1, you have to first transform this into an automaton that has a single final state. And once you have an automaton that has a single initial and a single final state, you can follow the same steps that we've done now. You remove the double arrows, you remove states that are neither starting nor final, and you repeat these steps until there's nothing to remove anymore, and then you read off the regular expression from the final automaton.